Okay, so if you did the exercise, you probably found that if you plot, make this nice. If you plot 1 over the concentration of C5H5N, right, which you can calculate because the concentration of iodine minus was given. So you first had to, that's of course a product. So you first had to use that from the initial concentration of 0.1 molar. You had to calculate the concentrations of the reactants and then plot that. And if you've done that, then you will get a straight line, with your data points on it, which means that indeed this is a second order reaction, and the slope of this curve is the rate constant, and in this case that is 7.52 10 to the minus 3 per molar per second. Right, so molar minus 1, second minus 1. Okay, so that was as far as the exercise goes. So that method, let's call this method 1, was looking at the different integrated rate equations. And just to repeat one more time, so I wrote it there. So if A minus X is linear versus time, of course, then N equals 0. So you have a 0th order reaction. If ln of A minus X is linear, N equals 1. And if 1 over A minus X is linear, N equals 2, right? So that's one method. The other interesting method is, let's call it method 2, is to look at the half-lives. So without deriving everything, there is a relation, which is the following: 2n minus 1 over kn n minus 1 plus 1 minus n ln A. So let's look at this equation, right? So this first term is a constant. The second term has the order n, and it has the ln of the initial concentration, so this is a constant, right? So if we would make a plot of ln t half versus ln A, so the initial concentration in ln versus the ln of time, and we would plot this. This would probably go down then the slope of this curve will give you n. Method 3 would be using the initial rates. So, okay, method 2 was using the half-lives. Method 3 uses the initial rates. Okay, so we can see that if we take the ln of the initial rate won't derive this, is ln kn plus n ln a. Okay, so that means if you measure the initial rate as a function of the reaction concentration, ln a, so the initial A concentration, you can easily find the reaction order by the gradient of this plot. Okay, so let's just on the side consider a reaction we looked, or an equation we looked at before. So dAdt is Kn times A. Let's call it P for simplicity, to not confuse with small a concentration, B to the Q, and C to the R. Okay, so this is some reaction which has different orders in A, B, C, which are P, Q, and R. So now, how would we get the reaction orders of those individual components using either method 1, 2, or 3? So one way is using the isolation method. So for example, I would put a very large excess of B, right? So over the whole course of the reaction, B is basically the same as the initial concentration B0, right? So if we then also take A and C the initial ones at least, equal, so they're stoichiometric, right? Then the reaction order, so what we will observe, becomes a bit simpler. So we have still Kn, we have concentration of B0 still to the power Q, and we have A to the power P plus R, right? Because A and C are stoichiometric, right? So now we can use method 1 or 2, keeping this large excess and measuring the concentration evolution of species A, right? So you will observe a reaction order of P plus R, okay? If we would do, let's say, a second type of experiments where we put both B and C in excess, right? Then the reaction will become Bth order. So by playing which of the reactants you put in excess, you can actually change which order you would observe for the different species, and like that you can determine the reaction order in each of the species. So an interesting point of method 3, which is why we're getting to this, is if you look for this example, so we have ln of the initial rate, in this case would be ln kn plus p ln a0 plus q ln b0 plus r ln c0. So to determine p, it's only necessary to find out how the initial rate varies with the concentration of A while keeping B and C constant. So in this experiment of method 3, you don't need a large excess of B and or C. So imagine you have a a reaction where you have limited solubility, or there are some experimental limitations of why you cannot use the isolation method using method 1 and 2, then you can resort to, for example, method 3. Okay, what's the effect of temperature? Well, you probably know this. So a reaction will usually go faster at higher temperature, right? But not always. And as we saw in class 1, there were some very good theories put forward, the most famous being that of Arrhenius, or let's say the most well-known one. We also talked about the earring, other things that we'll come back to later. But just to remind again, so in Arrhenius, if we draw a little energy landscape, versus the reaction coordinate, energy versus reaction coordinate, then we start with the reactants, right? We have our energy barrier, and we go to products. And this height here is the activation energy, right? So K equals A times exponent minus EA over RT, right? Or, of course, if we would put this in an alternative form, we take the ln of both sides, so we have ln K is ln A minus EA over RT. So if we would plot ln A would be the crossover if we plot ln K on this axis versus 1 over temperature here, we will get a line, right, with experimental values where the slope is EA over R and the crossing of the y-axis is ln A, right? And we'll see later that this A can be interpreted in terms of collision theory under specific conditions, that A is the frequency of collisions in the correct orientation. So you can imagine that molecules, they will bounce against each other, but they will only react at certain correct configurations depending on the mechanism, for example. So there are some statements I want to make related to this. There are reactions that are independent, that are temperature independent. Okay, funny story. People have found EA values that that are negative. So of course this can never happen. Cannot be true. So it means the mechanism is just more complicated. It's more complicated. So if you see negative values of EA, something is wrong. And the plot of the dependence on temperature can be curved as well. So it's not always a very simple relationship with temperature. So over the years, there have been, one of the relations that has been proposed, for example, to describe temperature dependence is ln k is empirical parameters, right? A, B over T plus C ln T. More recently, people started using ln k is A plus B times T to the power C. So again, these are at this point not derived from first principles, but it's just a way to, for a given reaction, and you want to know how it behaves at different temperatures. For example, in industry, it can be quite important. Then you can use these kind of relations to explain the reactivity. Okay, some additional comments. Okay, so again, Arrhenius parameters are empirically measured. But conceptually, okay, EA is the minimal energy needed to react. Okay. And this term, e to the power minus EA over RT, is the fraction of the Boltzmann distribution that have sufficient energy to react. So if we take that together, so A times E minus EA over RT is the fraction of collisions that lead to the formation of products.